Bismillahirrahmanirrahim and welcome everyone. Today we are going to start a very important topic of the gases, and that is the Vander Waals equation for gases, or you may say it as real gas law. We have already studied that there is an equation PV is equal to nRT, which is called as ideal gas equation. But this equation is only applicable to the perfect gases at all temperatures and pressures. And you know that the real gases that we come across in our daily life, they are close to the ideality only when the temperature is very high and pressure is very low. But at high pressure and low temperature, this equation does not remain valid for the real gases. So in order to uh, derive an equation for the real gases, we will have to modify this ideal gas equation. When the pressure in this ideal gas equation is calculated, this P, then the intermolecular forces between the molecules are neglected. Because in the ideal gas, you know that there are no intermolecular forces. And when this volume V is calculated for an ideal gas, in that case, the actual volume of the gas molecules is neglected. If we want to change this equation to a form which may be valid for all real gases at all temperature and pressure, then we will have to reconsider this pressure and volume. Or we will have to make two corrections in it. One will be the volume correction and other will be the pressure correction. So let us move towards the volume correction. Now let me tell you that in case of an ideal gas, actually we write the volume of, or the free volume, is equal to volume of vessel minus volume of molecules, actual volume of the molecules. In case of an ideal gas, this actual volume of the molecules is neglected. And if we consider that V free is equal to V, this one is the V which is used here, which is actually the free volume. But when we are discussing a non-ideal gas, in that case, this actual volume is not negligible, especially when a gas is highly compressed. So for a non-ideal gas, what will be the V free? That will be V vessel minus V molecule. Here this V molecule will not be neglected. Suppose that the volume of this room is V vessel and my volume is the actual volume. What will be the free volume available to me? That free volume will be the volume that will be equal to volume of vessel minus my actual volume. Because what volume I actually occupy, this is not free for other molecules to move in the same region. So V molecule is the actual volume, and this is that volume of a molecule which is not free for other molecules to move in. And in an real gas, for real gas, V free is equal to, suppose that V vessel is considered as V minus V molecule for 1 mole is considered as B. Now this B is not actual volume, rather it is called as excluded volume, because this volume will be excluded from total volume to calculate the free volume for the movement of the gas molecules. Or it may also be called as the effective volume, and its third name is the vibrational volume, or vibrant volume is also written in the books. And this is actually volume of 1 mole of a non-compressible gas. Non-compressible gas mean that the molecules are brought in the closest possible approach in case of a gas. You have compressed a gas up to the maximum value, and now this gas cannot be further compressed. That gas is called as the non-compressible gas. And the volume of its 1 mole will be called as the B. And actually, the B is 4 times of the Vm. Vm is the volume of the molecules, mean actual volume of the molecules. And there is a proof that I will discuss in some lecture that how B is equal to 4 Vm. In this lecture, I will try to restrict myself or to focus on the real gas law, how this equation is converted to a form which will be applicable to the real gases. What will be the units of B? It is volume of 1 mole. So its units should be decimeter cube per mole. These are its non-system international units, and meter cube per mole, they are its units in system international. And this B is actually directly proportional to the molecular size of the gas molecules. So this V free is equal to V minus B when there is 1 mole of the gas, and if we have certain number of moles N for a gas, then what will be the value of this V free? It will become V free is equal to V minus NB. So this one is the form of the free volume that we get after the correction. And in this form, we have subtracted something from that V, which was in the ideal gas equation. And this subtraction is actually of the actual volume of the gases. Now let us move towards the second correction, which is the pressure correction. Let me tell you that in case of an ideal gas, suppose that this one is the wall of the container and a molecule A is going to collide with this wall of the container, and there are certain other molecules here of the same gas. As there are no intermolecular forces, and this A molecule is not bonded to any other molecule through any kind of force, so that's why this A will strike with this wall with the maximum force, and the maximum pressure will be applied on the wall of the container. That is called as pressure of the ideal gas. But in case of a real gas or a non-ideal gas, we will have to consider the intermolecular forces. Now I am discussing the case of the non-ideal or real gas. This A molecule wants to collide with the wall of the container, but it will be bonded to some other molecules through certain intermolecular forces. As it is not free, So it will not be able to strike with this wall of the container with the maximum force, and it will not be able to exert as much pressure as this A molecule is exerting in the ideal case. And this pressure of the non-ideal gas will be called as P. And it is quite evident now that the pressure of a non-ideal gas is always lesser as compared to the pressure of the ideal gas. And why it is lesser? Just because of these intermolecular forces. So the pressure of non-ideal gas is less than the pressure of ideal gas. And how much it is less than? That is P lessened. Mean the pressure of non-ideal gas is less than pressure of ideal gas, and this pressure lessened is due to these intermolecular forces. So from here, the pressure of ideal gas will be equal to P plus P lessened. Mean if you will add this lessened pressure because of the intermolecular forces into the pressure of the non-ideal gas, then you will get the pressure of the ideal gas. And in the equation, PV is equal to nRT. Actually, this one is the pressure of ideal gas, and this one is the volume free. So this value of Pi, we will have to replace it here. But what is this pressure lessened? This pressure lessened is actually directly proportional to the concentration of the molecules A and B. Suppose that this molecule is A and these molecules are B molecules. Greater the concentration of A and B molecules, there will be more forces of attraction, and obviously due to more intermolecular forces, the value of this lessened pressure will be more. You can say that the concentration is N over V moles per decimeter cube. So pressure lessened is directly proportional to N square over V square. If you want to replace this sign of proportionality with equality, a constant A is used, A N square over V square. Now this is the value of this lessened pressure. Use this value here, so you will get that pressure of ideal gas is equal to pressure of non-ideal gas plus A N square over V square. So you can see that you have added something in the pressure for a non-ideal gas, and but during the calculation of volume you have subtracted some value. That subtracted value is the actual volume of the gas molecules, and this added value is actually the pressure which was lessened due to the intermolecular forces. When you will add this pressure into the pressure of non-ideal gas, it will become equal to the pressure of the ideal gas. What is A? A is actually coefficient of attraction per unit volume, and the value of A is directly proportional to the strength of intermolecular forces. What will be the units of A according to this formula? P is equal to A N square over V square. So A will be, let's rearrange this formula. A will be P into V square divided by N square. If the units of the pressure are atm and units of volume are decimeter cube, when you will take it square, it will become in the power 6 divided by mole square. So it will become atm decimeter 6 mole minus 2, and this will be its non-system international units. And if you want to calculate its unit in the system international, then you will have to change the units of the pressure and volume. So A will be equal to Newton per meter square. This one is the system international unit of pressure into meter cube square divided by mole square. And it will become Newton per meter square into meter 6 divided by mole square. And when you will rearrange it, it will become A is equal to Newton meter raised to power 4 mole minus 2. So this one is the unit of A in System International, while this one are the units of A in non-SI. So this one was about the A. Now let us conclude this topic that PV is equal to nRT. After correction, this pressure of the ideal gas is equal to pressure of the non-ideal gas plus pressure lessened. And after correction, this V is V minus NB is equal to nRT. Sir, this one is called as the Vander Waals equation or the ideal gas law. Now compare these two equations. You can see that you have if you will compare it, there will be some common features P, V, N, R, T. What is the addition and what is the subtraction? Actually, there are two values which are, you may say, introduced in this equation. That is the A and B. Said collectively, these are called as Vander Waals constants. While separately, A is called as the coefficient of attraction per unit volume and B is called as the excluded volume. Now these two A and B, these two constants are actually the quantitative measures of the non-ideality of a gas. Because greater value of A and B means more forces of attraction and more actual volume, so more non-ideal gas. Lesser value of A and B means lesser forces of attraction, lesser actual volume, so that will be close to the ideality and it will be comparatively an ideal gas. And if A and B are 0, it means there are no intermolecular forces, there is no actual volume, then this equation will be equal to this equation. That gas will be the ideal gas. And if you put the A and B 0 here, it will again become the ideal gas law. So A and B, they have huge significance in the sense that they are quantitative measures of the non-ideality of the gases. Usually, if the value of A and B are compared for the gases, you find that for all gases, the value of A is usually greater than value of B. And now let me tell you one thing, that if there is a single gas under different conditions and you calculate its pressure, the value of pressure calculated by this equation will be greater, while the value of pressure calculated from this equation will be lesser. Why? Because this will be the pressure of the ideal gas and this one will be the pressure of non-ideal gas, and I have already discussed that due to no intermolecular forces, the pressure of ideal gas is greater than the non-ideal gas. So if we can find some commonly observed gases, what is the order of their ideality according to the value of A and B? So hydrogen, helium is the most ideal, then hydrogen, then oxygen, nitrogen, carbon dioxide, ammonia, sulfur dioxide, and chlorine. Now, this one is the order of ideality of the commonly observed gases. Helium is most ideal, then hydrogen, and as we move away, then the non ideality increases. This order is very important for the MCQs, as the question arises that which gas is more ideal, which gas is more non ideal, or you may say what is the correct sequence of the ideality and non ideality of the gases. This one was all about the Vander Waal equation. I hope so that it will be informative for you. Inshallah, in the next lecture, we will come up with a plasma state. Till then, Allah Hafiz.